Welcome to physics. Today we're going to introduce the basic ideas of electric circuits. Last week we got a little bit into electrostatics with electrostatic force, but we're transitioning now from electrostatics into electrodynamics. And so your key parts that we're going to deal with today are electric potential, electric current, and electrical resistance. Let's start with electric potential. We can overall define it, and then we're going to talk about it conceptually. Electric potential is the ratio of the electric potential energy to the charge, or you can think of as the ratio of the work done to the charge. So in terms of symbols, electric potential is equal to the potential energy over the charge, which would be V for electric potential, PE for potential energy, and Q for charge. Or we could also write this as V is equal to the work over the charge. In the end, this is basically the number of joules per coulomb. So take, for example, if I had a positive charge here and a positive charge, these two charges will repel each other. So then I'm going to have to do work if I'm going to bring these charges together. So then if I do work, then I do work to change the potential energy, and each charge that I move together I have to do work on, and so then I would increase the electric potential, or the volts. In terms of units, volt is your unit of electric potential, and a volt is equal to a joule per coulomb. So volts are a commonly used measurement in circuits and electricity. So I want to take a minute to talk about applications in the real world. I'm sitting outside now because it's a really nice day outside, and I want to demonstrate what we just talked about with electric potential, which is also called voltage. Remember, we define voltage as a ratio of the potential energy to the charge, or the number of joules per coulomb. So I have a digital multimeter here that will measure voltage or electric potential, and I have a bunch of different batteries. I'm going to take a AA battery here, and let's meter this battery. So I'm going to touch the two contacts. Normally in class I would have a second person holding this, but I will do it on my own here. And when I meter, if you look at the meter there, we're reading about 1.60 volts. 1.60 volts means 1.60 joules per coulomb. So think about a battery. When you put a battery into a circuit, you put a battery in there to, say, light a light bulb or run something in a circuit. What the battery does is, inside the battery there are chemicals. It's a chemical reaction that takes place that converts chemical energy into electrical energy to push charges to flow. So if this battery rates 1.6 volts, 1.6 joules per coulomb, that means that it does work to push charges to flow in a circuit. Those charges that flow are able to do 1.6 joules of work for each coulomb of charge that is made to flow in the circuit. So if that's running, say, a light bulb, then you're able to get 1.6 joules of light energy for every coulomb of charge that this battery causes to flow. So when you're thinking about voltage and interpreting it, what you need to think about is whatever the number is in volts, joules per coulomb. If I take a different battery, let's say this battery, and I meter across the two contacts, on our digital multimeter there, we're reading about 8.02 volts. Well, this battery, if you can see it marked on the side there, is a 9-volt battery, which was in our smoke detector just a few minutes ago, but I needed a battery, so I took it out, and I'll put it back in a few minutes. So this battery is a little bit older. It's not quite reading 9 volts, it's reading 8.202 volts. So that means when I put this in a circuit, it causes charges to flow, and those flowing charges are able to do 8.02 joules of work for each coulomb of charge that is made to flow. If I take another battery, I did the AA just a minute ago. I'm going to take the AAA battery right now. And if I meter across this one, hopefully without dropping it, so we're reading 1.57 volts. A little bit of fluctuation there. If you can see on the side of the battery here, a AAA battery is rated on the side of it 1.5 volts. A AA battery is rated on the side of it 1.5 volts. A C cell battery is rated on the side of it 1.5 volts. A D cell battery is rated on the side of it. It's a little bit smaller there, harder to see. 1.5 volts. A's, B's, C's, AA's, AAA's, they are all rated exactly the same, 1.5 volts. What you vary in is the amount of chemicals that are in the batteries, okay? And by the different amount of chemicals, you have a chemical reaction that can occur. You still get the same number of joules per coulomb, but if you have more chemicals, you can react more joules or more coulombs of charge. So this battery has more chemicals. It can push more charge, or it might last longer than, say, this battery. In your 9-volt battery, you've got a different chemical reaction going on. This is an alkaline battery as opposed to a dry cell. And so this chemical reaction results in a different amount of joules per coulomb being produced. Electrical outlet. I'm going to take our meter and I'm going to switch the setting over. I'm going to open up our electrical outlet, which is another reason why I sat here, because I'd have easy access to it. These are designed to do this. So I'm going to meter the outlet. When I put the probes in there, we are reading about 121.3 volts, joules per coulomb. 121.3 volts means 121.3 joules of energy per coulomb of charge that is made to flow. So when I plug something in our electrical outlet, it causes charges to flow. Those charges that are flowing have the ability to do 121.4 joules of work for each coulomb of charge that is made to flow. Our batteries got that energy from chemical potential energy, from a chemical reaction occurring. Our outlet leads through the wires, eventually back to the electric company, whereby we produce electrical energy either by hydroelectric, where water is flowing to turn turbines to generate electricity, or we burn fossil fuels like burning coal to boil water into steam, and the steam turns turbines to generate electricity, or not around here but in different places, nuclear energy that we've talked about. A nuclear reaction to boil water into steam to turn turbines to generate electricity. So somewhere work was done on these charges to be able to give them energy, and when you hook up a battery or plug something into an outlet, those charges flow and do work on whatever is in the circuit. So kind of in summary, when you see a number in volts, what you need to think of is joules of energy per coulomb of charge, or joules of work that the flowing charges can do for each coulomb of charge that is made to flow. Now let's shift to electric current and start with a demonstration. Here we have a light bulb and a stopwatch. And what I'm going to do is start the stopwatch at the same instant that I plug in the light bulb. And I want you to tell me to stop the stopwatch when the electrons from the outlet have reached the light bulb. We're assuming this is a direct current application. I'm assuming you told me to stop. So I stopped at a time of a little over 1 second. I'm going to clear that and start again. Now I haven't stopped the stopwatch because none of the electrons from the outlet have reached the light bulb yet. So let's ponder what's going on with electric current. An electric current is basically a flow of charges, but specifically it is a rate. The rate of flow of charges past a certain point in a wire. So being a rate, that's a ratio of the quantity of charge to the time period. Let's pause for a second to check our light bulb and our timer. We're at about 40 seconds, and still not a single electron has made it from the outlet to the filament of that light bulb. So then in symbols, current is symbolized with an I, charge is a Q. This is a change in charge delta Q over time delta T. So then your equation to be able to calculate electric current, I is equal to delta Q over delta T. In units, you have charge in coulombs, you have time in seconds, and a coulomb per second is an amp or an ampere. The symbol is just the capital letter A. So if you have a current of 1 amp, you have 1 coulomb of charge flowing past a point in a wire each second. We have previously said that a coulomb of charge is a lot of charge. Well, an amp of current is a pretty ordinary amount of current. Typical incandescent light bulb, maybe 100 watt, you have about 1 amp of current flowing through that, or 1 coulomb per second. So now let's talk a little bit deeper about exactly what is going on with an electric current. Looks like we're at about 2 minutes and 10 seconds. Still not a single electron has made it from the outlet to the filament of that light bulb yet. So now let's picture what exactly is going on in that electric current. We have our electron here. It needs a reason to flow. So in order to run something, just like we did for our light bulb, we had to plug it in or we have to connect it to a battery. And the purpose of that battery is to supply a potential difference or a voltage across the wire. We'll say this end is our high potential, this end is our low potential. What happens then is that charge is going to be made to flow. Well, when it starts to flow, there's a problem. You have your solid wire that's shown here with all the atoms in it, and they're in the way. And so as our electron starts to move, it runs into an atom. When it runs into an atom, it's going to bounce off that atom and hit another and bounce. And as you can see, our electron goes through the wire, but it's not going very fast. It's not progressing forward very fast. It's not moving in a very direct route because it's running into so many things that are in the way. And so on our light bulb, it takes those charges a very long period of time to be able to move through that wire. So on our light bulb and timer, we are at just under 4 minutes, and still not a single electron from the outlet has made it to the filament of the light bulb. If we kind of arbitrarily drew that path, and I don't remember exactly the path that I took, so I'm going to draw kind of just a random bouncing path, but our electron travels and it bounces from atom to atom to atom in a very indirect path, running into lots of things in the process and not getting anywhere very fast. There are two different velocities we can talk about. The actual speed of that electron on one of those given yellow arrows. Your electrons are moving in the neighborhood of about 1 million meters per second. So if I highlight one of these individual paths, that speed of that electron is about 1 million meters per second. But what we're most interested in is kind of the forward progress velocity, and that's called the drift velocity. The very irregular path means that electron does not go very fast in that forward direction. That forward progress velocity or drift velocity for a typical wire is somewhere in the neighborhood of 1 millimeter per second. So it's not making progress forward very fast at all. If we ponder back to the light bulb and the stopwatch, none of the electrons have made it yet to the light bulb from the outlet because they just don't move that fast. So then why is the light bulb on? If none of the electrons have gotten to the light bulb, why is it lit? Why is it giving off light? Well, the thing we need to think about is where are these electrons coming from? They don't come from the outlet. They don't come from a battery. Those things are not really sources of electrons. Those things are sources of electric potential. In other words, your battery, your outlet, provides the push, the reason for the charges to flow. But those charges that are flowing are actually already in your wire. So then these atoms, and I'm going to steal my electron that I used a minute ago, these atoms have electrons, and when you establish that potential difference, those electrons that are already in the wire begin to move and flow and cause the light bulb to light. Prior to there being a potential difference or a voltage, those electrons are just moving around arbitrarily. If we were in class, we would have done this as a hands-on demonstration where I would have had one volunteer to be an electron, and we would have blindfolded that person. Two other volunteers, one to serve as high potential and one to serve as low potential, to guide the electron through the wire, and everybody else in class would have been one of those atoms, and we would have been sandwiched between two lab tables, and that electron would have to make it from one end to the other end, and that would be a time-consuming process because there's so much in the way. Similarly, back on our light bulb and stopwatch, it's just under 8 minutes, and none of the electrons have made it from the outlet to the film of the light bulb because the electrons move so slowly because the atoms get in the way. So now let's consider a couple of analogies to really understand what's going on in an electric current. So we have a wide open field. Down at the bottom, that's a stick figure of you. And we are going to put a blindfold on you so you can't see. You're brightly colored so you show up on various different backgrounds. So there you are in the middle of this field. So imagine we took the whole class, we blindfolded everybody, we put them in the middle of an open field, and I yelled go, and you started running as fast as you could. Well, if you picture that, that's what electrons are doing inside a wire when there is no battery, when there is no electric potential or potential difference. Those electrons just take off and they go and they move, and there are lots of them moving around in various different directions. And so they just move around. Now, this is a simplistic way of thinking about them. So a wire is not exactly like an electric field because a wire has atoms. So then to simulate those atoms, instead of a field, let's have a forest of trees. And now we're going to bring you and put you in the middle of this forest. Now imagine the whole class was blindfolded in the middle of the forest, and I yelled go, and you started to sprint. Think about what would happen. You would run bam, you would run into a tree and you'd bounce off. And then you start running again and bam, you'd run into a tree and you'd bounce off. And you start running again, bam, you'd run into a tree. And that's exactly what happens to electrons inside a wire when there is no battery or electric potential difference. They are moving around arbitrarily at about 1,000,000 meters per second, and they just run into atoms. This still doesn't represent a circuit because we don't have a potential difference. So then to change this a little bit to represent a circuit, I'm going to take our forest, and you got to use your imagination a little bit here. I'm going to take our forest and I'm going to rotate it a little bit. So now it's not just a forest, but it is a hill. Here is our electron, our person, starting out somewhere on that hill. Now, there is an electric potential, and the analogy to that is just like the hill. So now when the electrons move, it isn't quite arbitrary anymore, but those electrons are given a direction down the hill. The electric potential gives the electrons a direction. They go toward low potential. So here's our person, and they start to go downhill. Wham, they run into a tree. They bounce off. Wham, they run into another tree. They bounce off. Boom, another tree. And they keep running into tree after tree after tree. And it takes them quite a while to get down to the bottom of the hill. An electron does not move very fast in a wire because there's so many atoms in the way. They just keep running into thing after thing after thing. Okay, and then they get to the bottom. They get to the low potential end of the battery. And then what happens? Well, they go through that chemical reaction. And that chemical reaction brings energy back to them and brings them back to the top of the hill, so to speak, to the high potential. And then our person, our electron, goes through the whole process again and again and again. But keep in mind that the electrons are the electrons that are in the battery, in all the parts of the wire, in anything that is in the circuit. So then I just want to really emphasize your battery. It is not correct to think of it as a source of charges because the charges are really coming from everything that is anywhere in your circuit. Once you have that battery, that potential difference, then they're motivated to move in a certain direction. It's not an organized motion. It is rather chaotic as billions of charges run into atoms and kind of find their way through. So a battery is not a source of charges, but it is a source of the reason for those charges to flow. And that reason is that it supplies that electric potential or potential difference, the high and the low. Simplistically, you can think of this as the push. It motivates the charges to move in a certain direction, but there's so much there in the way, there's so many atoms, that when you have an electric current, it is very slow. They don't make forward progress very long. In fact, if we ponder our light bulb, none of the electrons have made it yet from the outlet to the filament of that light bulb by the sheer fact that the wire is too long. Based on the length of the wire and a simple V equals delta X over delta T term, those electrons will take about 30 minutes based on the length of that wire to be able to make it to the filament of the light bulb. So then back to our original question, why is the light even on if none of the electrons have gotten to the filament of the light bulb? Well, I want to emphasize again that a battery or an outlet is not a source of charges. The charge is already there in the wire, and so the light bulb goes on right away because the charges that are in the wire right next to the filament and in the filament are motivated to move. Now, once they move, and think back to the analogies, those moving charges run into atoms, and in running into the atoms, they transfer energy. That's what an electric current is all about. Motivate your charges to move, get them to run into things, and transfer that energy. And sometimes that energy transferred is expressed as heat energy, causing a wire to warm up. Sometimes that energy that is transferred is expressed as light energy in a light bulb. The light bulb gives off light. In a radio, that energy is transferred and sound is given off. And so it really depends on what the situation is as to what that energy becomes. But your battery, your outlet, motivate charges to move with a potential difference, and that energy transfer takes place. So an electric current is a slow thing. It's not about getting the charges to somewhere, but it's about motivating the charges everywhere in the circuit or the wires to move and run into things to be able to transfer their energy. So let's bring our light bulb to a close here. We're at just under 16 minutes. Still not a single electron has made it to the filament of the light bulb from that outlet. So what do we see when the electrons do make it to the outlet? Nothing different, because there are electrons already there that are colliding and producing light. If we waited for 30 minutes, which we're not going to do, it would look exactly the same as it does now. One more piece I want to throw into the picture, and that's Ohm's law. And this brings together our electric potential and our electric current. The more electric potential, when this becomes greater, that means that you're going to motivate more charges to move. You're going to have a higher electric current. And these are proportional to each other. We have a direct proportion or a linear relationship. Our proportionality constant we call resistance, which is basically conceptually the opposition to the flow of charges. And that's what you saw in terms of the atoms getting in the way, the trees getting in the way. And so then if we set up an equation, the ratio of V over I is equal to constant, remembering that V is your symbol for electric potential, I is your symbol for current. And so that constant is then equal to R, which is resistance. So we have the equation V over I is equal to R. Oftentimes we will multiply the I to the other side and write V equals I times R. And this is your Ohm's law equation that brings the different quantities we've been talking about together. Now, resistance, your unit of resistance is an ohm, which has a Greek letter omega. Now, let's consider this example. We have a fluorescent light bulb, 26 watts, 120 volts, operates on a current of 0.22 amps. So first of all, just identifying what these different things are. 26 watts, that's the power. And so basically that means a watt is a joule per second. 26 joules of energy are being converted into light energy every single second. 120 volts, that's the electric potential V. And 0.22 amps, an amp is current, so that is I. So then in part A, how many electrons are moving each second due to the current in the bulb? Well, that's going to be a picket fence. 0.22 amps, remember what an amp is. That's a coulomb per second. And so then once we think of that in coulombs per second, we can convert into electrons, because we know one electron has a charge of 1.6 times 10 to the negative 19th coulombs. So that's going to give us 1.25 times 10 to the 18th electrons. Each second, that's how many electrons are moving through the wire. That's 1,000,000 trillion electrons moving through the wires, moving through the light bulb every single second. Now in part B, we really want to think of this 0.22 amps and exactly what it means in terms of, is it a how far, is it a how fast, what that means. Well, we know, again, the units, that's coulombs per second, and coulombs per second relates to a number. So then when you're dealing with a current, it's a number of charges that are flowing. So then let's say we had a higher current. Let's suppose we had a current of 10 amps. That does not mean that the electrons are moving faster. That does not mean that the electrons are moving farther. What that means is that there are more electrons that are moving. So current is not a speed thing. It's not a how far, it's a how many. Larger currents, more charges are moving. Smaller currents, less charges are moving. But there's not really any significant difference in how fast those charges are moving. Now let's consider part C. Well, we can use our current equation, I equals delta Q over delta T, because what we want to find is how many coulombs of charge. So then my I value is 0.22 amps. My time period is 35 seconds. And we want to solve for delta Q. So then putting that over 1, if we solve down for delta Q, the charge value what we get there, 7.7 coulombs when we multiply 35 by 0.22. Part D. Calculate the resistance of the bulb. Knowing our voltage and knowing our current, we're able to use Ohm's law for this. V is equal to I times R. For V, we put 120 volts in. I is 0.22 amps. And then our resistance is the unknown. So then when we divide, we will get a resistance of 545.45 ohms. Now, there's one other thing I wanted to talk about that'll come up in the problem solving, and that's the idea of the quantity called a milliamp hour. Well, if we think about a milliamp hour, a milliamp, that's 1/1000th of an amp. An hour, well, in seconds, that's 3,600 seconds. So then in units, an amp is a coulomb per second. And essentially, I am multiplying this by a second because it's a milliamp times an hour, not a milliamp per hour. So coulomb times a second would just leave you with coulombs. And so a milliamp hour is actually a unit of charge. But it is commonly used with batteries. And the reason is because in a battery, you have a fixed amount of chemicals. And if you have a fixed amount of chemicals, that means you have a fixed amount of charge that can be pushed as a result of this chemical reaction. So let's say, for example, arbitrary number here, battery. A battery is rated 1,000 milliamp hours. Well, you can convert this into a number of coulombs, and you'll do that in the homework problems, but it would be a fixed number. If that's a fixed number, milliamps times hours, in terms of our equation, I equals delta Q over delta T. If I solve for delta Q, that would be I delta T. So that product of I delta T is equal to a constant, and that means that you have, at least for a battery, an inverse relationship here. So then on our 1,000 milliamp hour battery, well, I might be able to have 100 milliamps running. And if I have 100 milliamps running, that's going to last for 10 hours. Or maybe I have 1,000 milliamps running. Well, then my battery is only going to last for 1 hour. And so you can do some mental math because one goes up, the other goes down, but the product is going to remain constant. with that value of milliamp hours. And so that is used oftentimes with different batteries. And you'll explore that more in the problem solving.